Good afternoon to all. The topic I'm going to talk about is how secure is channel fragmentation, aggregation, and bonding in wireless networks. Most of the talk focuses on this, and towards the end I'll touch upon few aspects of some other work I did. So this is going to be the outline pretty much. I'll talk a little about dynamic spectrum access, security threats in dynamic spectrum access, and focus specifically on service disruption attacks. The main problem formulation, what we found, and where to go from there. So this is, please pardon the picture, I couldn't get it bigger than this. So this shows how the FCC has allocated spectrum for different bands. Now, for those who are unable to read, some of these are like the wireless band, some are like Wi-Fi, some are like the ISM. It's as big as I could make it, but really this shows pretty much how FCC has allocated spectrum over the United States. Now, what happens is when we do the actual spectrum measurements, this was made in New York City area in the 54 to 88 megahertz region. As you see, the red ones here are actual usage. There is signal, and the white part shows that this spectrum is not used. So there are some parts. Is there a pointer here I can use?
No. There is no laser.
That's okay. I can use the board.
Yes.
So if you look at this portion, this is unused for a period of about 80 milliseconds. In fact, this is like 100 milliseconds. So that's sufficient time actually. 100 milliseconds of a spectrum not being used. So what happens here is essentially what we are seeing is these empty spaces are called white spaces. And the idea is, can somebody use these white spaces? Because this is a licensed band. And we are seeing 54 to 88 is the TV band actually. And if there are some portions where it's not used, now obviously we cannot have somebody purchase a TV band for that period of time, but what can be done is somebody can just steal that spectrum for this duration. The idea is this. Many applications always need more bandwidth, and they are also non-uniform. They are elastic. The demands are elastic. And there are some who have the bandwidth but don't use it all the time. What currently happens with that first picture I showed you with FCC spectrum allocation is a static allocation. So the TV cannot operate on a cellular phone band, even if it's available, because they are not supposed to be doing it. They have been licensed only to use the TV band. Now, obviously, fixed spectrum policies are not efficient or not the best thing to do, because there are white spaces which could potentially be used by others which are not being used. It's just left idle. The solution is dynamic spectrum access. The term cognitive radio was coined by Joe Mitola in the 1990s, mid-90s, and that was based on software-defined radio and an adaptive map. But the dynamic spectrum access pretty much came in around the same time, the 97 period, where people started looking at borrowing spectrum which is unused by licensed users. So how this the whole thing works is you periodically send spectrum bands for holes, which is the white spaces, and the licensed primary users have access priority to that band, but the unlicensed secondary users who don't have priority can borrow that band when it's not in use, but with the agreement that they evacuate. The last line is not clear. It says evacuate as soon as the primary is sensed. So as soon as they sense, they keep sensing periodically. If they see that there is primary signal, they have to leave the band. Now, what does this do? This is a very flexible way of operation, meaning anybody can use any frequency band as long as it's available, which is obviously a good spectrum utilization, but brings with it some problems. And the problem is it brings with it some other vulnerabilities, which are not normal to any wireless network in general. The kind of denial or the vulnerabilities here are pretty much either you are denied service or you have a poor service, which is like service disruption. This could happen to primary users or secondary users. Now let's see how it happens to primary users. A primary user suffers if a secondary user doesn't leave when they are supposed to leave. And that can happen due to two reasons. One is the secondary user just has a sensing failure. It senses but is not able to really read the signal properly or makes a wrong spectrum decision and continues to stay when it is supposed to leave. The other is the Byzantine attack. Now that happens because of this. So we have a primary transmitter somewhere here, and let's say people in this region can hear the primary transmission. Right? This could be like a TV tower. Now, this node A is well within that region and can hear primary transmission. But node B is outside this region, but let's say it can talk to A. Then what B does is it depends on A's decision for its own purpose. So it questions A like, what do you think? Is primary on or off? And whatever A says, he believes. Now this means A could potentially, give a wrong information to B. And A could just say it's not there when it is actually there. B would start transmitting, and that would disturb the primary receivers in this region. That's one kind of a Byzantine attack on B. On secondary users, there's one kind of attack called the primary user emulation attack, where a bunch of malicious users, they start mimicking the primary. So they transmit signals which are like primary. So this node A would assume that primary is on when it is really not and would leave. That's one kind of denial of service. Now, the Byzantine attack could also work against B, meaning when the primary is off, A could say it is on and prevent B from even accessing the spectrum. So that's another kind of attack on B. The last one is what we will be talking about is call quality degradation by active service disruption. I'll tell you what it is as we go further. This one type is by jamming. You could just jam a channel, right? But we are not talking about jamming here. We are talking about a specific attack due to channel fragmentation, aggregation, and bonding. I'll first explain what channel fragmentation, aggregation, and bonding is, and then I'll come to why that could cause a service disruption. Feel free to stop me at any stage if you have a question. Now, of course, that FAB is fragmentation, aggregation, and bonding. And this is what happens. The first thing is fragmentation. Let's say we have a 6 megahertz TV band, or any band for that matter. You could split that 6 megahertz into 3 bands, typically 3 bands of 2 megahertz each. So instead of, usually what would happen is somebody would be allocated one 6 megahertz band. Instead we fragment it into 3 parts and give somebody only the 2 megahertz. Why this helps is if the requirement is not really 6 megahertz, you don't want to give an entire 6 megahertz to one user. You could give it to 3 users, having them as sub-bands. The other thing that can be done is bonding, where you take 2 contiguous 6 megahertz bands and bond them into a single 12 megahertz band. Right? So we would, instead of having F1 and F2, we would have an F1 prime centered at that frequency, having a bandwidth of 12 megahertz. Channel aggregation is also kind of bonding, but you don't necessarily need contiguous bands. You could take this 6 and that 6 and give somebody 12. The 802.22 standards for wireless regional area networks, they specifically talk about how all these can be achieved. And this is not just specific to cognitive radio networks, even the LTE and HSPA plus networks, they define fragmentation, aggregation, and bonding. The LTE and HSPA really don't talk about fragmentation, they only talk about bonding. Pretty much bonding. They do define aggregation, but it's not used that much. Now, why does this cause a leakage? Because once the bonding is done, if the standards, the way they specify is, even after doing fragmentation or aggregation or bonding, if you do the cyclic prefix and other things correctly, it should result in orthogonal channels within that network. But what happens is, for example, an LTE network with bonded channels could cause leakage into an HSPA network and vice versa. So that is not really taken care, even the way they define it. Same with the 802.22. This can result in a leakage which can be exploited by a malicious user to cause service disruption. Can I bring it down or up a bit?
It's okay.
Because the last lines are getting cut off. I don't know.
Yeah, I don't know why.
We did some experiments on this. So what we did was we took some 802, wireless LAN stations, which was running on the 802.11 ABG hardware, and we bonded the 5.24 and 5.26 gigahertz channels, right? And we saw what was happening in the 2.4 gigahertz. Now, this picture here, this portion actually shows the actual signal power. And it is superimposed, don't compare them on scale, it's superimposed with the leakage from, what happens is we have two stations, one operating in the 2.4 or that band, and another at the 5.9 band, which these two bonded. Both are transmitting simultaneously, and we are seeing what is received at the 2.4 band. So here we see this shadow here shows the leakage power. And in terms of percentages, I'm not sure how clear this is, in terms of percentages, that's a good 40 to 50% extra. So it's not a negligible kind of signal we see. And we didn't observe this when the bonding was not there. So initially we even thought that this could be something else, but we found that when we do not bond, this shadow never appears. It's only this picture. And when the bonding takes place, this happens. So there is leakage due to bonding on other channels. And this is the question, can this be analyzed for service disruption attacks? This is different from jamming in the sense, for jamming, let's say I want to attack somebody who's on frequency F1, I have to transmit on F1. But here, because of the leakage, I can transmit on F2, and the leakage can cause service disruption on F1. So it's sort of a little more dangerous than jamming, because you sense a channel, you think there is nobody, and you start using it, and somebody transmitting elsewhere can affect this. Now, we analyze specifically two types of attacks. One is, let's say the malicious attacker has no constraint. He has a constraint on the maximum power, but he can go to whatever. He's really not running out of battery in that quick pace. So let's say he's allowed to use as much power as he wants, as long as it is less than the maximum. Okay. The purpose is just create as big impact as possible. So we call it the maximum impact attack, or the MAXIMP. Then the other option is you transmit at minimum power, but just create sufficient impact. So that is called the MINPOW attack. We look at both of them. In the MAXIMP attack, what we are looking at is, since we really don't know, what I mean by that is, let's say there are 10 users. A certain power level P1 can create impact for user 1, but not necessarily for user 2. So he wants to transmit as high as a power as possible, so that on an average everybody is impacted. Almost everybody. Whereas in the MINPOW attack, you just transmit enough so that you attack the users enough to create a loss in the signal to noise ratio, or the throughput. Just to give a numerical example, let's say the amount of interference that's needed to create a loss in the signal to noise ratio is of the order of, let's say, some 10 dBm. Now, in the MINPOW attack, you transmit just enough power to cause that 10 dBm interference. Whereas in the MAXIMP attack, transmit as much power as possible. The interference could be 10 dBm or even more. There, the idea is you reduce the signal to noise ratio so much that the entire channel capacity gets affected and people think that this channel is not good to use. In the other case, there is somebody already transmitting and you attack only those people enough to give them an impression that they want to leave it and look for some other channel. So to formulate this problem, this is what we have. There are n channels and each one fragmented into k fragments. So there are totally n k fragments. In case of bonding or aggregation, the n becomes like n minus 1 if two channels are bonded. And the objective is to allocate signal strength in each channel, that is this EI here on each channel I, so that you either create maximum impact or minimize the transmit power. And what we know is the correlation between channels. Fragments are orthogonal, that correlation is 0. The same thing when formulated as a formal optimization problem looks like this. So the average leakage is 1 over nk summation Li square, which turns out to be maximize this function over E is the vector of signal strengths, such that that constraint is satisfied. E Hermitian E is less than equal to E total. Just rewriting this in terms of the eigenvalues, it changes this problem into something like this. Maximize summation lambda I di square, where lambda is the eigenvalues of this matrix, subject to summation di square less than this. This is just, I'm formalizing what we mentioned in the previous slide. Just notice, in this case, the constraint is on summation di square, the objective is summation lambda I di square. In the MINPOW attack, it is the other way. The constraint is on summation lambda I di square, the objective is summation di square. Now what happens is these two are not duals of each other, so solving one doesn't really solve the other. The key results are this, that is, in both cases, these constraints have to be met with equality to create, to obtain the optimal solution. Which means, in the MAXIMP attack, you use all the power, that's what I say. Right? Use the full power. And in the other case, stop when that epsilon, when that minimum interference level is reached. And the actual value, the real, the exact signal strength which we apply on each channel is given by this, where x1 is the eigenvector corresponding to this lambda 1, the biggest eigenvalue. And the actual value of the impact depends on lambda 1. So lower the value of lambda 1, we find that the impact is better, lower, as well as the transmit power is higher. Which means, from the attacker's perspective, lower lambda 1 is a disadvantage, because when the attacker uses its full power, the impact is very small. And if the attacker wants to create impact, it has to transmit at very high power. So from the attacker's perspective, a small lambda 1 is bad, but from a system's perspective, a small lambda 1 is good. So we'll see what these interpretations are. Like I said, the smaller, the largest eigenvalue. So it's the whole problem of, if I want to now pose a different question, what is the best way to do the fragmentation or bonding or aggregation? Then the solution for that would be, do whatever you can to minimize the largest eigenvalue. So min-max problem. But having said that, it's a very simple statement, but it's an NP-hard problem, because we are now looking at, say, n channels, right? It's an n cross n matrix. Now, I can do anything with these n channels. I can aggregate anybody, I can fragment anybody, I can bond anybody. So I have to see all possible combinations of fragmentation or aggregation or bonding that is going to give me the smallest value for the largest eigenvalue, which is a very, it's a discrete optimization problem, and it's NP hard. We really don't know upfront what would be the best solution. But sure, given two solutions, we can use this to compare, which is better. That's what I meant by saying that it adds significant complexity to the design of wireless networks, because now we cannot just fragment or bond whichever channels we please. We have to take care of this factor here. Now specifically, what does these two attacks mean? The MAXIMP attack, the attacker is using the full power, so it is more likely to be successful. However, it's not so energy efficient, meaning it because it uses full power all the time. The MINPOW attack is more energy efficient because it uses minimum power, but in many cases the attack may not even be successful, meaning even with that power, it may not create any impact for a user. This is one numerical example. What we did was we took the 802.22 network with 3 channels with 3 fragments each, as defined in the standard. And what we see here, don't worry about these values here. What is of interest is, in order to create any impact with this kind of power distribution, like the total power we take is like 2 watts. With this kind of a power distribution, 5 watts, not 2. With this kind of a power distribution, we are able to see that you have non-zero powers on every channel, and this can create impact on any channel you want. And why does this result in more than the others? Because of the very nature of the correlation. Probably channel 4 is not as correlated with the others. And overall, how much impact can it reduce? So when I increase the total transmit power, now though the x-axis says 20, it's unrealistic to assume that a wireless handheld device can transmit 20 watts. But what we can do is, suppose let's say there's a group of malicious users instead of one. Then together they can aggregate their power to give that kind of value. And there is a steep increase. So beyond a point, the rate at which the loss in the channel capacity could be of the order of, say, 180 kbps. This is for .22 networks with 3 channels. When we do it for a .11 kind of a network with 13 channels, right? Here the loss is even bigger. It can go as high as 7-8 Mbps. That's quite a significant loss in the capacity. For the MINPOW, we didn't take the .22, we took more of like an LTE HSPA, because that is where we were looking at throughput. See, there we looked at loss in the capacity. In the previous slide, we were looking at loss in the capacity. Because in a .22, what happens is you're looking at a set of secondary users. You don't know how many, we don't know what they are going to do with that band. We just want to keep it as small as possible so that the secondary users avoid this band, so that the malicious ways can use it all for themselves. In this case, we know exactly where people are, like they could be close to the cell, far away from the cell, we know what modulations they are using. And here we are comparing LTE and HSPA in terms of loss of throughput. Remember that in the MINPOW attack, we are causing enough interference, right? There is an epsilon term there, which is the minimum interference, to make the user feel a disruption in service. And that interference directly translates to a signal to noise ratio, which translates to a bit error rate and hence a loss in throughput. So, of course, here some of these numbers seem really big, but these are more of simulation results. Like for the LTE, for example, the far users can suffer as big as 70% in throughput, whereas this number is sufficiently small for HSPA. Again, the reason is because we pick the correlation values from what is given in the web for these channels, which is why these kind of numbers come in. That doesn't necessarily mean that LTE systems are bad or they're not good to be used. It just means that for far users, the LTE users suffer more than HSPA. And then we took intermediate users, which are like the 16 QAM users. The near users, the HSPA guys suffer more. So it's just based on the actual spacing of the frequencies and how they are correlated. It has nothing to do with the design of an LTE or design of a HSPA system. So this is the key observations we saw, which is in .22 networks we have about 11 to 16% loss in the capacity due to channel fragmentation, aggregation and bonding. Whereas in LTE HSPA the loss is in throughput. Now, even though the numbers are exaggerated, like 16 and 70, right? In the first case it's capacity, so it is 16% of 54 Mbps, which is a very big number, as compared to say 70% of say 200 kbps. Okay. So in terms of percentage they look blown up, but in terms of actual rates it's probably comparable to what happens. And this implies that we have to really choose carefully which fragments we want to use or which channels we want to really bond or aggregate. So the channel fragmentation aggregation problem, which is currently specified as just pick two channels of 6 MHz each and you will get 12 MHz. That's not really true. We are looking at mitigation of the attack because I mentioned that this problem of choosing the perfect channels is an NP-hard problem. But what best can we do? Like, is there some suboptimal solution and how it works is what we are looking at. This work was, the first part was presented in ICC 2011 and the second one, the LTE HSPA work, was presented in Globecom 2011.
So this channel correlation is reflected by the eigenvalue, right?
Yes, yes.
But the maximum eigenvalue is maximum.
It should be the smallest.
Yeah, I mean the maximum eigenvalue reflects the strongest correlation between.
It reflects the strongest of all the correlations. So among the correlations, the maximum eigenvalue reflects the strongest component of the correlation. So which is why if they are perfectly orthogonal, even the maximum value will become 0. And hence, there's no real impact.
So this correlation depends on not only the frequency partitioning, also the filters and the other vectors. Like what are the?
Right, it depends on the filters, the properties of the cyclic prefix. It depends on the frequency partitioning, and it depends on certain other parameters. Like some of them use equalizers and all that. It's a function of everything. So the correlation is not a simple inner product.
So
it's
how
not.
do you get those values?
Those values we actually got it. There is a particular web page on the LTE standards where they did talk about how they measure the correlation. So we just use those expressions to construct the matrix for that center frequencies. Any questions on this part before I go to the next part? Now that concludes what we were doing on the channel fragmentation. That's one kind of security vulnerability in wireless networks, which is specifically due to channel fragmentation and bonding. Some of the other research which I'm working on are these, and we specifically focus on these topics. On covert timing channel, collaborate, this is in social networks. So in wireless networks, I work on secrecy capacity, location of the eavesdropper, primary user emulation, and covert timing channels. And in social networks, these are some of the topics I'm investigating. I'll stick to these three in this presentation. And if there is interest and if people would like to know more, we can take it up. Okay, let's see what covert timing channels really mean. Let's say Adam is a transmitter and he wants to transmit to Bob, and there is Ed, who is the eavesdropper in between, who's trying to catch what these two are talking. Now notice the timing here. It says, hello Bob, I am Adam. The difference between Bob and I is large. See, now R started almost immediately after Adam. There's a difference in the delay between successive packets. So this is like, between hello and Bob, the difference was like 1 second. I mean, in a real example, we really don't delay by 1 second. I kept it as 1 second because we wanted to see the difference on a presentation. If I had kept 100 milliseconds, we wouldn't have been able to see anything. They would have all just flashed past. So in a real system, it will be like 30 milliseconds and 50 milliseconds. But essentially what I'm saying is between hello and Bob, the difference, the interpacket delay was like 1 second. But between Bob and I, it was 2 seconds. Right? So this pattern of 1 second, 2 seconds could mean a bit pattern like this. So apart from this message, hello Bob, I am Adam, are you listening? Adam could have transmitted that bit sequence 011, 100011, whatever, and Ed would not even know that this has happened because it's not in the message, it's actually in the interpacket delay. Now, this is what is called as a covert timing operation because it's dependent on the interpacket delay. The other kind of covert communication is called the covert storage communication, where what happens is, let's say we transmit a packet and there are different headers. Let's say Adam purposely messes around with few bits in specific headers. Now if Bob sees that these headers are messed up consistently, then that could itself mean a message. Anybody has experienced this Trojan horse virus in your computer anytime? The Trojan horse is an example of a covert storage channel.
But you're going to admit it. I'm going to admit that you had that.
Yeah. If anybody has experienced it, that's an example of a covert storage channel. Now, covert storage channels, because it involves changing particular information in a database, it's sort of a little risky. Even the malicious guys who want to use this for their communication, they're sort of worried about it. The timing is a much simpler operation in terms of this delaying packets. Now, even though I said that this delay is good enough to transmit some information such that Ed won't even know, Ed can know in some sense. Let's say this is an experiment we did. We just had some wireless LAN station sending some FTP packets, and we just counted the intra-arrival time between packets. Now, because of the fading wireless characteristics and all the multipath and everything, you'll never have a consistent interpacket delay. It's going to be random. But there's a peak around the mean, and the rest of it is distributed like this. In fact, we did some more, with the larger number of packets, it can be approximated by a Gaussian. This is when there is no covert communication, just normal FTP. But let's say we delay the packets corresponding to say 35 milliseconds for a 0 and 65 milliseconds for a 1. If I do that and send some covert communication underneath, the packet count distribution looks like two distinct Gaussian distributions. So if an eavesdropper just keeps sniffing the packet count and starts building the distribution of them, the histogram of them, then he knows surely that this is strange. I mean, why is there one peak here and one peak here? Then sort of makes a guess that probably something is going on. Now, the others, the network can sort of camouflage it. This experiment, what we did was, we had 5 separate transmit-receive pairs, each one not just transmitting FTP but also covert communication underneath. Now if you look at the packet count distribution, it looks very similar to the case when there was no covert communication. So what happens is the others can effectively camouflage each other. But this is if the eavesdropper is using a very simple naive detection mechanism, which is just sniff the packet. The eavesdropper can become smarter and start doing better things. The network can become smarter and start doing some more camouflaging. Instead of just putting 10 more FTP communications, they can do other things. Now, we are not getting into details of what exactly they can do, but let's assume that the eavesdropper, the smarter the eavesdropper is, he can put more resource in sensing. And let's say the smarter the network is, can put more resources in terms of camouflage. In terms of a DSA network, what this means is something like this. Let's say there are 5 channels here, and in each of these channels, a set of users want to transmit data with some covert communication underneath. Now, the attacker, he is sensing all these channels. The attacker has a limited resource, meaning when he is sensing channel 1, he cannot sense channel 2 simultaneously. So probably he has to divide in terms of time, or let's say he can do it simultaneously, he has to put different powers on different channels so that the sensing is better on different channels. So the amount of sensing resources on each channel could be the time, could be the power, and it could be any other resource, like how many people are focused on how many channels. But let's say at the end of all this, based on whatever the sensing is done, the network is also trying to camouflage, one of them is going to win. Let's say the attacker thinks that these 2 channels have covert communication going on. Then what he does is he just jams those 2. Now, from the network's perspective, they can do any amount of camouflaging and they can prevent the sensing, but once the jamming takes place, they have no means of preventing anything. They just have to live with it. It's almost like this, when a bunch of, let's say I'm walking with a lot of money in my pocket on a very lonely street, and I know that there could be some muggers around there. Right? The best thing I can do is I can sort of walk in such a way that they don't see me or they don't know that I have the money. But the moment they spot me and they decide to catch me, there's nothing I can do other than just give my money. It's like if they spot me, then I can't do anything. But I can do my best so that they don't spot me at all. So what can the network do? How does it deploy its auxiliary resources to camouflage effectively? From the attacker's perspective, how does it deploy sensing resources to detect effectively? So this is a zero-sum game because one of them wins. From the network's perspective, you minimize the maximum impact. And from the attacker's perspective, you maximize the minimum impact. So that's one part. And after this is done, we then form a non-cooperative, non-zero-sum game where the attackers decide how much powers to put on each channel. So when I said this sensing and camouflaging is through auxiliary covert communications, they are all on the same channel. So then what happens is the overlay, the main FTP communication could be disturbed because of having other people communicating. So there is interference they cause to each other. So this is a 3-stage problem. How do we sense? How do we camouflage? Then how does the attacker allocate powers? And then what does this do to the overlay communication? I'm skipping details of what we did because it's an entire sequence of problems by themselves. But just the key results, this is what we found. That, normally a simple allocation of sensing and camouflaging resources could be that, let's say the impact, which is measured as loss in capacity, right? Suppose, let's say the impact is highest on channel 1, next on channel 2, third highest on channel 3, which means channel 1 is the channel where my most, vulnerable and very important communication is going on, or my highest data rate communication is going on. Channel 2 is the second, channel 3 is the third, and so on. A simplest allocation strategy would be a linear allocation strategy, right? Just take the impact divided by the total, take what percentage and then allocate it there. What we are seeing is, compared to that, the sensing and jamming game, the way we do it with our non-zero sum and zero sum game, it not only results in less loss for the network, it results in higher power for the attacker. So it actually protects the network better. And if you look at what it does to the overlay communication, we find that the smaller the packet time, then the covert timing operation is better, which means it yields better throughput and it has better robustness. But what does smaller packet time mean? Either you increase the data rate or you keep the packet size. So typically the covert communications are better off under high rate application like a video streaming than say an email. And it's also better under ping or a kind of small packet application than FTP. In fact, we found that YouTube video is a very good tool if you want to really send covert messages. So you could sort of hide a file under a YouTube video and have people extract without even being detected.
Found any examples of that?
We do have one in our lab. We tried something. Actually, we didn't try it for the covert problem. We tried it for a steganography problem.
Okay.
And we found that we can't really hide a picture under YouTube, but you can hide, let's say, 1 page worth of data on under a YouTube video with sufficient without being detected.
Did you analyze the bandwidth of the covert channels here, the maximum bandwidth? So how would you compare the wireless covert channels, say the covert channels on the IP stack?
In terms of the bandwidth that you can, there's absolutely no comparison. In a wireless covert channel, the kind of bit rates we are talking about is like 100 bits per second, not more than that. So we are really not, like I said, that file of 1 page under a YouTube video is not under wireless. If it was wireless, there was no way I could transmit 1 page worth of information as a covert. These covert operations I'm talking about is, let's say a maximum is like a 16-digit credit card number, where someone doesn't even know that a credit card number is being sent. Those are the kind of things that's possible in wireless. Whereas, like you said, in a real IP network, it could be really huge. I could send a picture or, sufficiently at least a 1-2 page document. So we started this way back in 2009, and then we had one in Infocom, and recently in JSAC of Jan 2012 we had one publication of this. And these are available on my website. If anybody wants the paper, just send it. Now, in social networks, I do find that some work related in WINLAB is talking about collaboration in ad hoc networks. Is that right, Professor? There's some work on collaboration in ad hoc networks, right?
Not from a social network.
Not from a social network perspective, I understand. But I wanted to present this to see if there is any relevance to that kind of work that goes on. Yes, specifically looking at, these are several problems we saw, like how do users deal with confusion, how information flows in a social network, and how does a population grow, and like altruism and several aspects. Right now I'll just talk about these two. If there is interest, we can talk about any of the others also. What we are talking about collaboration here is something like this. Let's take a Twitter page, and let's say someone starts a topic on this. And initially there are some 5-6 people actively participating. And after some time, what happens is some new people join the discussion. Some people who are already discussing, they just leave. And maybe they come back later, but I treat them as a new person when they come back. Now, this is like a chat room, right? If I just leave this door open and people walk in and walk out as they please, the number of people in the room is going to vary dynamically. It's going to be some number, some people come in, some people go out, and so on. So let's say we have an initial mass of like N0 people who are discussing on a topic, right? And we want to grow this to some value like n star, typically greater than n0. One is, what are the factors that affect this? Yeah, suppose I start a group or a movement. It could be as a movement as serious like the Occupy Wall Street, or it could just be a group where we say, hey, let's start an interest group on social networks. Right? So for this interest group, let's say we are like 10 people in the group, and we say, okay, by the end of February, let's say we want 50 people, right? Or not end of February, let's say we just want 50 people in the group, so that this group makes its presence felt. Like people think this is a serious group, and they take our activities and what we say seriously. And we want to grow from 10 to 50 as early as possible. Now what I can do is, if I start this group individually, the best thing for me would be to go to each one of the people here and say, look, this is a group which I plan to start, would you be interested? And sort of show the benefits of how it can help if we form a group like this. Let us say one person gets interested, and let's say we decide to grow this together to 50. Now intuitively, obviously when two people work towards it, the time is going to be faster than I alone trying to bring it to a strength of 50. But the unfortunate part also is that people who have currently joined can suddenly leave and say, hey, this looks like it's not going anywhere, so I want to leave this group. So that then takes me a step backward and I have to start again. So how do I, what is it that is going to help me grow? One is the amount of activity, like how many people do I talk about on a daily basis? If I talk to only one person every day, and if that person keeps refusing, then my chances of success is small. However, if I talk to 20 people every day, right? Even if 19 people refuse and one person accepts, my group is growing. And the other is my popularity index. If I am a kind of person whom everybody trusts, and they believe, hey, this guy is saying maybe there is something. If I am that kind of a person, then when I talk to 20, let's say 10 of them join. But if I am a kind of person who nobody really wants to work with, if I talk to even 50, nobody might join. So that is my popularity index. So these two factors affect the speed at which the growth takes place. But when we have multiple people, everyone has a different popularity index, everyone has a different activity level. So now the question is, how can we work this in a heterogeneous context? And how much of work I allocate to each person? And each time I collaborate with somebody, there is a cost involved, meaning I'm taking somebody's help, which means I got to pay that person in terms of a monetary pay, or I have some kind of obligation, like somebody helps me, it puts me in a situation where I have to help that person back if needed. So how is this cost going to affect this collaboration as such? That is what we are going to study in this problem. And we just did a first passage time Markov analysis to solve this problem. And these are what we saw. We verified this against actual data obtained from Twitter. So we took data on some popular topics, and this experiment was done in 2010. So at that time Haiti was very popular. So a lot of people were tweeting on the earthquake in Haiti. So we looked at, we characterized some of the parameters using that and verified that our model was agreeing with what we saw on Twitter on Haiti. We saw it for the number of tweets sent to President Obama.
So what is the group here with respect to Twitter?
It's not really a group. It's almost like if you take Haiti, for example. And first of all, we do some natural language processing to get rid of some outlier kind of tweets. If someone says, I'm going to Haiti on vacation, I'm not counting that.
Sure.
I'm only counting the earthquake on Haiti. So what we do is every minute, let's say I'm looking at how many people are tweeting on Haiti. In the first minute, let's say there were 50 people. In the next time scale of a minute, I look at, let's say there are 55 tweets instead of 50. I first see who are the people common between the two, right? And I don't count them. I only count the new ones. So these will be like new people entering the discussion. And if there was somebody in this 50-50 who did not tweet, I count them as a death. They just left the discussion. So the group really is that number, that's all. So we do have a transient in that, it doesn't start with 50. So it's like, when we first did the experiment, there were like 4 tweets or something. And with time, let's say we ran this experiment for a whole month. For the 5th or 6th day, this number went to like 50, 60. So we then look at, starting from some initial number like 100, how long does it take for this whole string to reach say 120 or 130, 140 and so on. So the group really is about the topic, it's the way we do. In Twitter, it's very difficult to define a group as such.
Yeah, so maybe I'm a bit cynical, but I'm not sure how much discussion is there going on.
Well, Twitter has a limit on the size of the message, so even the discussions are going to be like short messages. But we saw that over the month, at least, see, if I do the same experiment today, probably there will be nothing on it. Right? Because the topics in Twitter usually have a very small shelf life, like it's about a month, month and a half. Sometimes if the topic, like Occupy Wall Street has a long amount of, since last November we collected data and we are still getting sufficient data.
So, so did you calculate like differ from retweets or from or like?
No, we ignored retweets.
Okay,
we ignored retweets. We ignored the same person. We are looking at how many people are interested. So if one person did not really retweet but just posted 100 tweets, but it's the same guy doing it, we ignore that also. So we are trying to see how many different people are doing it. So we are trying to see how many different people are getting interested on a topic. Of course, like you said, it's not really representative of the interest on IT really. But from a perspective of verifying a model and collecting data, the best we could do was look at some topic which is where people are really tweeting. I mean, the ideal way to look at interest would be to do a survey. That's the real better way because we have questions which are tuned to determining interests. And how does some of our work apply to wireless or cognitive radio networks is this analysis can be not directly applied but with some modifications can be used to see how parochial societies evolve in cognitive radio networks. And it can also be used for something like cooperative packet forwarding in ad hoc networks. Because each one is using somebody else's resource to forward packets.
So you're saying this result come from Twitter analysis, right?
Yes.
So it's like you see the gain and the cost. What is exactly the gain is the number of people who join the discussion, right?
Okay, gain, when I say more gaining by collaboration, it's something like this. We talked about the popularity level and activity level, right?
Yeah.
So let's say I put a threshold of 1 to say anybody whose popularity is less than 1 is not so popular, and anybody whose popularity is greater than 1 is popular. Now this popularity, the way we define it, is the ratio of the number of people entering divided by the number of people leaving. Okay. So that means if the ratio is less than 1, it means people leave faster than they enter. Okay, that means I'm not so popular. And if people enter faster than they leave, that means I am popular. The case of exactly equal is a degenerate case. We are not looking at that. Now here, when I say less popular, for those whose popularity is less than 1, the growth is faster if I work in collaboration with others than working by myself.
Okay.
Whereas if I'm more popular, if I'm greater than 1, then the growth is actually faster if I work individually than working with somebody else. This is something we saw in our experiment.
So the collaboration itself is analyzed based on how many people like a comment on the same topic continuously?
Yes.
Like, what does it mean is collaboration? If I comment once, does that mean I'm also a collaborator?
If you are commenting once, it means that you could potentially be a collaborator.
Okay.
But if along with your comments, let us put it this way. Let's say there are more replies to your comment, right? Suppose the kind of comment you are bringing in is making other people interested, and say, let's say after you started commenting, let us say more tweets started pouring into the topic, related to, replying to what you are saying. Then it's almost like you're collaborating with me to increase the popularity.
Yeah. So maybe we should talk offline.
Yeah. And the other thing, in this case, what we saw was the objective was to reach a particular threshold as early as possible, right? Let's work the other way. Suppose I gave everyone a deadline and I say, okay, you got to reach this number by, say, end of Feb or end of March or whatever, right? Now, it can still talk about collaboration, right? You can still collaborate to reach that deadline. Just to differentiate between collaboration of the first kind and second kind, I call this altruism. Though in the classic definition of the word altruism means I'm helping somebody without expecting anything in return and at my own cost. I lose to help somebody. But here that doesn't really happen. Somebody collaborating with somebody else is not really losing all the time. Here it's almost like I help somebody reach their objective, and in the process I reach mine too. It's that kind of help, not really the thing. I mean, it's almost like a big, like Bill Gates being a philanthropist, right? He has reached what he wanted to reach financially, and now he's in a position to give to other organizations, right? I mean, by doing charity, Bill Gates is not losing his bank balance, or at least he's not bankrupt. So that is the kind of altruism we are looking at. Now, here what happens is, apart from the capability or the popularity what we have, there's also a deadline for which the task should be achieved. Okay. Now, the collaboration makes sense only if I help somebody achieve their task before the deadline. Now we are seeing how much of my resources I spend on doing my own work and how much of my resources I spend on doing somebody else's work by extending help to others. And that extended help is what I call as altruism. For this, we couldn't really measure it through Twitter data. So here we looked at TBLP authorship data. So here we are saying that if I co-author with somebody, I'm sort of being altruistic, which is not true because I'm getting a benefit too. I'm getting a publication to my name as well, right? Real altruism is if I work on somebody else's paper and tell them, hey, don't put my name on it. But I can't have a means of measuring that. I don't know who helped without having their name. So the only way I could measure it was by the co-author. And assumption here is the second or third authors are helping the first author to do their work. And that usually happens, right? The advisor helps a student and so on. So that is how we measured. We formulated this as a Stackelberg game and verified it against some DBLP authorship data. Here also we find that the more altruistic somebody is, they actually benefit more. Again, benefit as how we define. So, it's like how much you gain by helping, what is the cost. And it also, there is one more factor we took into account. Sorry, let me go back to the previous slide for a minute. Here we have a new term called difficulty level. Now what this means is, for example, if someone wants me to help with a paper on, say, journal on communication systems or something, which is not so popular, which doesn't have a high impact, which has a higher acceptance rate, as against a paper like Nature Science, right? Then my effort for both are different. Even though my capability and all is the same, it's a more difficult task to get a paper in Nature Science than in, say, journal on communication systems. So, of course, we have to quantify that in terms of how difficult the task is. So that is something actually my tendency to help somebody would actually decrease, or the amount of help I can extend to somebody would decrease if that task is more difficult. So it's that much difficult for me to help within my capabilities. So the application to wireless, again, we can do it for cooperative packet forwarding, and we can also use this for cooperative spectrum sensing, where we can divide the sensing time between a lot of people. And that's all I had in this presentation. I'm open to questions.